This time let me talk about Wronskians. Wronskians of functions. The word Wronskian comes from the name of a person. There was a mathematician whose name was Wronskian, and the thing that he made up was Wronskians. It's a way to easily figure out whether given sets of functions are linearly dependent or not. See, we could prove by some words of these two given functions are linearly dependent or independent, but that often takes too long. So Wronski thought of a way to almost mechanically show that two given functions are linearly dependent. Okay? So let's see how he did it. So let's think about the following question. Are sine x and cosine x linearly independent? Yes? No? Are they linearly independent?
Yes.
Yes, they're linearly independent, right? Yeah. Okay, we know, but here's how Wronski approached it. He did the following. If they are really linearly independent, you're saying that c1 times cosine of x plus c2 times sine of x is equal to 0 for some non-zero solutions. Oh, no, you're saying that this is true for only for c1 and c2 both being 0, okay? Okay, so he looked at this and said, well, you know what? This is not just a regular equation for x. It's a functional equation. So when you're writing down, you're claiming that this is true for all values of x. That's what you're saying, right? And then he said, well, when two sides are equal as functions, then their derivatives are the same. Did you know that? Let's see. X squared plus 2x plus 1 is equal to x plus 1 squared. Right? You all know that, right? This is an equation of functions. These two sides are equal for all values of x. In that case, we can differentiate the left side and we differentiate the right side. 2x plus 2, 2 times x plus 1, and they still agree. Okay? That's true. Their derivatives, I can differentiate and they still agree. Now, let me ask you a different question. Suppose I wanted to solve x squared equals to 2x. Okay? I actually know what the solution is. But x equal to 0 and what's the other solution?
X equal to 2.
Yeah, 2. 2 squared is 4. 2 times 2 is... Okay, so 0 and 2 are the two solutions, right? Okay. Now, suppose somebody came up with this question and said, okay, I want to solve this by differentiation. I differentiate the left side, 2x. Differentiate the right side as 2. So x is equal to 1. Is that right? No, that's not right. I know that the solution is 0 or 2. This is not a solution. That's the wrong solution. So what is this person doing wrong here?
Those functions aren't equivalent.
These are not equal for all values of x. Okay? This is a functional equivalence. This is not a functional equivalence. The x squared is a function that's like that. 2x is a linear function. These are different functions. Is there any reason for their derivatives to be the same? No. Okay? So there's a very big difference between saying that two functions are equal and saying that they're equal for some value of x. Okay? This is some point that it's often overlooked. It's not always true that you can just differentiate and still set both sides equal. But for here, because we're claiming functional equivalence, we can differentiate both sides and say c1 negative sine x plus c2 cosine x, and say these two should still hold. All right. Now we're going to change the viewpoint of this system. We're going to treat x as some constant, and we're going to treat this as system of equations for two unknowns, C1 and C2. Does that make sense? Right? C1 and C2 are those numbers that we want to find out, and cosine, sine, these are some constants. Okay. Now, that means I can rewrite this as a system of equations in matrix form. What's the matrix of coefficients here? What should I write? Okay, so two unknowns are C1 and C2. What should I write here?
1.
This times that, right? So what should I write here?
Cosine X.
Cosine x,
Sine X.
sine x,
Negative sine X.
negative sine x,
Cosine X.
cosine x. Okay? And what do I put here?
0, 0.
0, 0. So we put it like this, and we try to solve this using matrices. How do you solve this using matrices?
Kramer's rule.
You can use Kramer's, right? Or yeah, you can use Kramer's, or you can invert this matrix and multiply it to the other side, right? Do you know that? You can move this C1, C2. Inverse of this matrix times 0, 0. That's the answer. Okay? Now, this actually achieves something. If you look at this, whatever this matrix is, by the way, do you know how to invert 2 by 2 matrices? We actually need this later on in the course, so let me write it here. It's 1 over AD minus BC. These two get switched. It's D and A, negative B, negative C. So that's what it is. Okay. So we can use that formula to invert this. It will be still a 2 by 2 matrix. And you can multiply this, and what will be the result?
The values of C1, C2.
Yeah, but can you predict the result, even without actually computing this? It'll be 0, 0, right? Because whatever this matrix is, if I do a cross down, this times 0, this times 0, it'll be 0, right? A cross down, it'll still be 0, okay? By the multiplication of matrices, it'll just give me 0, right? And we've achieved something. What did we achieve? So let's go back and see how this thing works. It's like this. We're saying the only way for this to be true in a functional way is for this to be also true, and when you write them as as this equation, you've proved that C1 should be 0 and C2 should be 0. And if you, I said that linear independence means the only way that this is possible is when C1, C2 are forced to be 0. What is linear dependence? If there are solutions to this equation with at least one of them non-zero, right? That is equivalent to saying that the only way that this can happen is when C1 and C2 are both 0. And we show that that's the only way because we solved it. So this is a way to show that these two functions are linearly independent. Okay? Because if for this to be true, the only way is for them to be both 0. All right. So that was the initial reasoning that we can think about. And then you go back and think, well, what is the core logic here? What makes us to force C1 and C2 to be 0? And you have to think more, and you will understand that for this kind of argument to work, this should exist. Now, do inverse of matrices always exist? No. When does it not exist? When this is 0, right? What is this thing called?
Determinant.
It's called a determinant, right? This is a determinant of A, B, C, D. Okay. So here's what's happening. If that is non-zero, if it's non-zero, we can come up with this matrix, and it will be forced to be 0. So actually, there was an important part that we overlooked. For this argument to really work, we have to show that this does exist, because it's not always true that inverse matrices exist, right? So we have to really try to compute cosine x, sine x, negative sine x, cosine x. We have to take their determinant, right? So let's do the determinant. It's cosine squared of x minus negative sine squared of x, and therefore it's cosine squared of x plus sine squared of x. What's that?
1.
1. And therefore it's not 0. Therefore this exists. Therefore C1, C2 are forced to be 0. Therefore these two functions are linearly independent. Okay? So that's the entire argument. Okay? And at this point, you can just extract the core part of this argument and come up with the following important result, which is it's like this. Let's say you're given fx and gx. You want to see if this is linearly independent or dependent. Okay. What you do is you do the same thing as this, right? And then you write the next one by differentiating it, right? And the coefficient matrix will end up being this one exactly, right? And what are we interested in? We can strip out all the arguments and say, really, what's at the core of the problem is, does this matrix determinant become 0 or not? Okay. So it's like this. If it's not 0, what did we find? The same argument allows us to say that fx and gx are linearly independent. Okay? If this is true. And if they're 0, then you know that fx, gx are linearly dependent. Okay, this argument I didn't explain clearly, but it will also turn out that if this is 0, then you have some non-trivial solutions to the original equation where not both of them are 0. So that's something in linear algebra. But I don't want to go that deep. Okay? I mean, as long as you're convinced with this, that should be good enough. Okay? So that's basically. Oh, by the way, there are two ways to write down determinants. Sometimes you write DET in front of the matrix. Sometimes you write down these two bars. That's another representation of determinant. Okay, so I'll try to use this notation. Okay. So let's see the power of this. Okay, e to the x and 2e to the x. Are these linearly dependent or independent? Dependent. We know that because one is a multiple of the other. Now let's see what the Wronskian tells us. Okay. By the way, this thing is called a Wronskian, and it's represented as W bracket with e to the x. Sometimes semicolon, some books use commas, e to the x, semicolon, 2e to the x. And what is the Wronskian? You write down the two functions and you write down the derivative. In this case, it's the same. Now try AD minus BC. What's that?
0.
0. So what does that say?
Linear line dependent.
Okay. That's a lot easier than trying to show linear independence and dependence by writing a bunch of words. Okay. Lastly, let's think about the Wronskian of cosine x, sine x, and e to the ix. Are these dependent or linearly independent? Is this set linearly independent or dependent? Huh?
Dependent.
It's dependent because I can represent this as the sum of these two with some coefficient. 1 times cosine x plus I times sine x. It's dependent, right? So we expect the determinant to be what? 0. Yeah. It will turn out that way. Okay. So what we do is we write down cosine x, sine x, e to the ix, right? And then write down the derivative, negative sine x, cosine x, I e to the ix. Now the problem is, if we stop here, it's not a square matrix, and determinants are only defined for square matrices, right? So what should we do? We differentiate one more time to make it a square matrix, okay? We differentiate one more time. It's negative cosine x, negative sine x. It's negative e to the ix. Actually, we're taking the determinant. And for 3 by 3, you have to do row expansion or column expansion, right? Let's do expansion of the second row. It doesn't matter, but let's expand it this way. This negative sine x times sine x e to the ix, negative sine x, negative e to the ix. Okay, and then you need to put a minus because of the checkerboard of signs, minus plus minus, right? The checkerboard of signs should give you minus plus minus. So this is plus cosine x. Let's see, cosine x e to the ix, negative cosine x, negative e to the ix. Then finally you have minus I e to the ix, cosine x, sine x, negative cosine x, negative sine x. If you do this, you're going to see that every one of these small determinants are 0. Okay? This times this is same as this times this, right? So when you do this times this minus that times that, it gives you 0. Same thing, this times this is same as that times that. This times this is same as that times that. So all of them are 0. So you get 0. So it's very convenient. We didn't even have to know Euler's identity to check that these three functions are linearly independent. How nice is that? Suppose you didn't learn Euler's identity. You can still use the Wronskian to prove that they are linearly dependent. So it's very powerful. That's all I have for today.